issue. Okay, thank you for the nice introduction. And my name is Jee-Hwan. Today, I'd like to introduce a few soft robotics technology that our lab currently conducting and their application to construction robotics. Okay, before I get started, I would like to briefly overview some of the research topics that our lab currently doing. We have four main research topics. The first one is haptics and telerobotics, mainly focusing on stable and control aspect. So we've been working on stable and high performance telerobotic system for the application of construction automation and space robot application and military application. So we have a long-term collaboration history with German Aerospace Research Center. So the video that you are looking at is space astronaut. So the human operator on the Earth can teleoperate, remotely control the space robot in International Space Station, even 500 millisecond communication time delay with haptic feedback. So we have demonstrated through the teleoperation, even on the communication time delay, the human operator can do kind of dexterous manipulation tasks that astronaut in International Space Station has to do. So that shows some possibility, I think. And the second topic is soft actuator. We call tendon-driven muscle-like actuator, named it twisted string actuator. And based on this actuator, we are developing and working on wearable devices like exoskeleton for construction workers. And the third topic is soft growing robot. Inspired by plant and root, we are developing soft continuum growing robot for the application of disaster response and construction and medical applications. So I'll talk more detail about this. And the last but not the least one is autonomous vehicle. So this is often I said hobby project of myself and my students. Whenever we have some extra time after done 3 of the research above, we enjoy developing autonomous vehicle, mainly for participating autonomous vehicle competition. So many years of hobby project, we finally won in the autonomous vehicle competition 2019 organized by Hyundai Motors. And among them, today, I would like to focus 2 soft robotics topics. The first one is soft growing robot, and the second one is twisted string actuator and their application for construction robotics. Okay, so let's get started for the first one first. Soft growing robot, we call it vine robot, has been getting a lot of attention because of their unique locomotion. We call it moving by growth. So basic principle is really simple. Let's say there's a tube, and if you invert and provide the air pressure through the channel, then it continuously grows as the material provided to the tip. So by using this principle, we can make a robot which can grow and steer. So that's why we call soft growing robot and vine robot. The principle is really simple, and it has many advantages and great feature. Because of its unique locomotion, it grow, not move whole body. So it can move without being affected by the environment. So whether environment is sticky, slippery, it doesn't matter. It can grow. And it can navigate through narrow space, narrow gap, because it grow, not moving. And also it can climb, it can move. Any issue? All right. You can move vertically. So you can climb up wall because it's intrinsically very lightweight. And thanks to those advantages, okay, right? Yeah. Thanks to those advantages, there are numerous potential applications. One of the first motivation that we started this research was to develop disaster response robot. So we believe this type of robot can navigate narrow space, like a narrow hole, like a building collapse like a situation after disaster or earthquake. So it can localize buried disaster victim and provide some air or water or some emergency food until first responder reach to the target. So that's the first motivation that we started, and this is the simple demonstration that we made. And another interesting application is colonoscopy. How many of you got colonoscopy, inspection? So many of you, maybe during sleep, right? Because it's uncomfortable. It's uncomfortable and gives a lot, discomfort. And the intrinsic softness and the moving by growth nature actually minimize the influence or effect to intestine. So we could make a new type of colonoscopy. So we are currently working on a new type of colonoscopy with a medical doctor in Seoul National University. And another interesting application could be exploration. So exploring, coral reef or natural heritage, because it minimally give an influence to the environment. So those are the potential application and many others. And typically in this presentation, I would like to more focus on the application for construction. So our city urbanized. So rapid urbanization lead to a complex network of underground structure. So whenever we need to build new tunnel or new hole, there are many problems actually present, like road disclosure and damage to pre-existing infrastructure. So there has been a large demand for directional excavation to avoid damage to pre-existing underground structure. To do this, we need high curvature and small curvature radius when we make a new tunnel. So that's the motivation for our research. And the left one, the figure on the left, shows the conventional drilling machine we call tunnel boring machine, in short TBM. It has cutter head in front and cylinder connected to each segment to provide a steered directional drilling. But it has mostly rigid component and straight rigid body part. So it shows poor steering functionality. Usually, it's known that the maximum curvature, minimum curvature radius that it can achieve is usually larger than the 9 times of the cutter head diameter. So which is quite big. So if you want to make high curvature turning angle or small curvature radius, it's actually not possible to achieve this. So we by replacing the thrust part with the bind robot, soft growing robot, we propose new concept of directional excavation machine. And there are 3 components we need to develop. First, flexible propulsion module, and second, excavation module, and third, discharging module. First, about the propulsion module. Inspired by plant, we developed a new type of soft propulsion module. In this propulsion module, we use a little bit different growing mechanism. The first one that I introduced was eversion-based growing mechanism. So invert the tip and provide the air, but this mechanism is a little different. We use material is provided from the base through the roller, around the roller. And the air pressure from the base provide a propulsion force. So it's a little simpler than the eversion-based growing mechanism. And for this, we need to think about the material, because the material should be soft enough to bend around the roller and provide an airtight function. And also, it should be robust enough to endure the wear out, between the friction and interaction or with earth. So we selected fire hose, which we believe soft enough and robust enough to satisfy all those functions. And for the excavation module, we got inspiration from tunnel boring machine. So this is the typical tunnel boring machine structure cutter head. But usually tunnel boring machine has single cutter head in front, because the rear rigid part is robust enough and provide big enough rotational torque. But the soft growing robot behind actually couldn't provide robust enough, counter rotational torque. So we need to introduce 2 cutter head in front, which rotate opposite direction to automatically balance out the rotational torque. And maybe later on, we can use this, two directional speed difference to make a turn in three directional. And last, but this is also very important, Mach discharge module is also very important because without discharging those Mach, we cannot find the space to move forward. So we introduced Mach discharging module. Basically, we spray water from the top and retrieving the soil after soil water mixture through suction at the bottom. So that's typically what tunnel boring machine have used. And in order to test the feasibility and the performance of our directional drilling machine, we prepare experimental setup, like you see in the slide. We prepare wet compacted soil with water contents of 11 to 40%, which actually give us the hardest environment. So it's not actually easy to drill out. And by providing an equal air pressure between those two valve, we achieve straight directional drilling, straight drilling. And we alter the rotation speed of motor and also the pressure to see the penetration speed, to check the penetration speed. And we found there is not much actually big curvature change, the gradient change. But the average penetration speed was about 6 to 8 millimeter per minute, which looks like very slow, but this is actually typical directional speed of tunnel boring machine. So not that slow. It shows good enough performance. And by introducing some air pressure difference, we could achieve directional steering, as you can see. So 18, 41, and up to 40 or 50%, 51 degree directional drilling was possible, as you can see. And by introducing a little bigger pressure difference, we could achieve like a 50 kilopascal. If we provide a 50 kilopascal pressure difference to thrust module, we could achieve about 90-degree curvature angle, as you can see. And it's interesting to see that this intentionally produced buckle actually help us to achieve 90-degree directional steering. And the curvature radius was 42 centimeter. And the cutter head radius was 20 centimeter. So it's about 2.1 times larger than the cutter head diameter. Considering that the conventional tunnel boring machine should have 9 times larger curvature radius, and conventional soft growing robot, soft mechanism-based directional machine has the smallest curvature radius was like 7.6 times larger than the cutter head diameter. So 2.1 is extremely small, compared to any other directional drilling machine. And by pulling one of the thrust module, we could achieve even smaller curvature radius, like 1.9 times, only 1.9 times larger than the cutter head diameter. So that's the smallest value that we achieve, and probably the smallest value in the world. And you may notice that this mechanism actually couldn't provide enough supporting force to the excavated channel and tunnel because it has open structure. It simply has two holes. So recently, we developed a new inner channel securing mechanism based on the inflatable tube structure. So we made 6 inflatable tubes, and each inflatable tube we make individual everting-based fine robot grow. So by doing so, we could achieve the inner channel, secured inner channel. So we can use this inner channel for multiple purposes. So as you can see in the video, this robot can grow and even steer, and we can use some of the tool through the secured inner channel. And it's robust enough and provide big enough supporting force to secure the excavated channel. So that's our latest research, and we are planning to combine this module with our excavation module. All right, so that's the first part, and move on to the second part, to the twisted string actuator. So many of you already know construction labor often suffer from musculoskeletal disorder, and low back injury is the most frequent reported cases. So a lot of company and research institute are developing wearable exoskeleton or wearable robot to support these construction worker and reduce some social cost produced from this injury. But most of the wearable devices are exoskeleton, not exosuit. That means it's mostly composed of rigid body, rigid component. So it's good to provide high assistance force and bandwidth and precise control, but due to joint misalignment and significant inertia and low back drivability, it provides huge discomfort to the wearer. So they do not actually want to wear while they are working. So a lot of actually researchers and people working on exosuit, which is like a suit, flexible and lightweight and comfortable. So it's lightweight, portable, and provide a comfort. But the limitation is there's a limitation to provide a force, and also control accuracy is very low. So even though it's comfortable, but it didn't actually provide enough supporting force. That's the problem. And one of the very important question is what type of actuator is good for this type of exosuit, and how to provide a big power and high control precision. There are many soft actuators, tons of soft actuators. Among them, our lab has been working on twisted string actuator for many years. Probably, many of you already heard of twisted string actuator. The concept is really simple. Let's say there's a string, bundle of string. If you twist it, it contracts. So with small torque, we could achieve large contraction force. Basically, this is a transmission system. So installing motor one side, we can use this as an actuator. That's what we call twisted string actuator. We've been working on this twisted string actuator many years. There are many advantages. Probably those two videos shows the biggest advantage. It has very high power to weight ratio. That means this motor is only 20-watt motor, but lift up 30 kilogram easily. Okay, this video. Yeah, like this. And it can transmit power over arbitrary curved surface. So it doesn't need to be rigidly aligned in straight. That means by installing motor backside, you can transmit power over the shoulder, over arbitrary body shape, along arbitrary body shape. So that's very interesting feature. And we have compared, luckily, we have a chance to compare our actuator with many other different types of soft actuator, like a SMP, SMA, IPMC, SCP, and even hydraulic, and so on and so forth. And interestingly, this is our actuator, twisted string actuator. Twisted string actuator shows quite comparative performance compared to other existing artificial muscle-like actuator, soft actuator. Even this is human. For the right, this is human muscle. Compared to human muscle, twisted string actuator actually shows really great performance, comparative performance. In order to fully take advantage and use this feature, great feature, we need a lot of background to study. So precise kinematic modeling, precise dynamic modeling, and high bandwidth control, position control, not only position control, but also tension control, and also not only position and tension independently, bidirectional, simultaneous position and tension control was necessary. So we have done those research. Actually, those are all published. But due to the time limitation, I probably cannot cover all the topic. Integrating those ideas, we've been developing many different types of twisted string actuator-based exosuit. The first one that you're watching is hip joint exosuit for supporting construction worker. It's about 4.5 kilogram, but it can lift 15 kilogram weight support. And thanks to the efficiency, the current battery system, battery is actually built in, battery system can last about 4.5 hours. And the second one is fully soft exoskeleton for rehabilitation, fully soft elbow and wrist exoskeleton for rehabilitation. And the third one is about 1.5 kilogram or 1 kilogram upper limb exoskeleton to support logistic worker or or child garden farmer to lift up some weight. It's only 1 kilogram, but can support about 10 kilogram weightlifting. And the last one is fully integrated hip and knee and ankle exoskeleton with a single actuator. We are currently working on this one. And this presentation, even with short time left, I want to talk about a little more detail about the shoulder exoskeleton for construction worker. Nowadays, there are many construction workers who need to lift up heavy weight of tool and do some many hours of overhead operation in shipyard and construction environment. And it gives a lot of pain and a lot of muscle fatigue. So many people, many researchers working on passive type exoskeleton, which installs spring backside. So gravity compensated passive exoskeleton. But this passive exoskeleton has also a lot of issue because operator need to manually tune the levels of assistance every time when they change the type of tool. And also they need to first move against the spring force. So that's not actually good for them to wear. So recently, people also start working on quasi-passive exoskeleton, which can autonomously or automatically tune the stiffness for adjusting the weight of the tool. So that's quasi-passive exoskeleton. But also the question is what type of actuator is suitable for this? And we found very interesting phenomena and very interesting mechanism by twisting rubber, not synthetic fiber that we've been working on twisted string actuator. For conventional twisted string actuator, we twist synthetic fiber, non-stretchable synthetic fiber. But in this research, we twist rubber, basically, kind of spring. And we found when we twist rubber, stiffness increase with the amount of rubber twist. And even more interesting thing is energy is only used when changing stiffness. While we are, holding this position, we don't need to apply any motor torque at all. So that's really good. So by installing two, and we call it TRUST, Twisted Rubber Stiffness Tuner. And by installing two TRUST at each shoulder, we were able to make a shoulder exoskeleton, which can provide 8 Newton meter of torque to the shoulder, which is really good, really big, with only 2.4 kilogram lightweight. So I believe this is the, shoulder exosuit, which has highest power to torque or highest power to weight ratio. And it consumes minimum energy. When we need to change the status, we only apply motor torque, and rest of the case, we don't need. So I asked my students how long this current battery system run. Then he said, whole conference hours it can run. And for high-level control, we used VLM-based stiffness adjustment. So the camera is installed, here or here at the chest, and we train the visual language model, and camera recognize the tool and recognize the weight of the tool and automatically adjust the stiffness based on this trained model. So user don't need to actually care about the stiffness tuning. So as you can see, when the system recognizes hammer and stapler and drill, it actually automatically tuned the stiffness. I brought demo over there. So during the coffee break, if you want to interact more detail or want to see the performance, then you can try on this. So there's a demo over there. And this study will be presented as well in ICRA Expo Thursday, I guess. and Friday workshop, VLM workshop, Visual Language Model workshop. If you want to know more detail about the VLM method, you can also attend this one. So let me summarize my talk. So in this presentation, I introduced two soft robot technology, soft growing robot technology and twisted string actuator technology, and their application to directional excavation, which I believe shows great promise with the highest curvature steering angle, and thrust-based quasi-passive exoskeleton, which shows the highest power to weight ratio. Right. Thank you so much.
Thank you. Thank you, Dr. Ray. It's so interesting. And two different topics also very